to the cloud.
Okay. So I'll start now. Hi everyone. So I just I met a few of you last time. My name's John Hardy. I'm based in Melbourne in Australia. I came to FORTH in the early 80s, but never really had an opportunity to use it that much. But I recently started to get back into some of the things I was doing in the 80s, including 8-bit computing, some Z80 stuff. And I was a little bit frustrated with assembly language, which was something I hadn't done for quite a long time. I had to relearn it. And it was quite an interesting process because I got fast at it again. In fact, I ended up, I think, getting better at it than I was at the time. But I was sort of interested in, you know, higher level programming. In the last 35 years, I've been doing other things. And in the last 25 years, I've been doing web development primarily. So I was wanting to look at virtual machines that I could implement. And then it came back to me that FORTH is a virtual machine that is quite easy to implement in a few K. So as a sort of a project I started to be interested in, I started implementing a version of FORTH in the Z80. I'm not the first person to have done this, but it was really a case of, I find the easiest way to learn something is to just get in there and start doing it. And I think it's a pretty common path in FORTH is many people have implemented a version of FORTH. Not everyone, but a great number of people, when they come to an unfamiliar platform, they start working in FORTH. So I implemented that. So I'll just share my screen anyway, and let's see how we go. Can you see my screen?
Yes.
Right. Okay. So just to give you a sorry, I'll just get that out of the way. Yeah. So what we have here is an emulation of. Yeah, I'm just giving you a little bit of a background. My talk will be brief today because I haven't been able to complete all the things that I was hoping to complete. Now, I'm just wanting to make sure, am I sharing the correct screen? What are you people seeing? Because I can't see.
We are seeing a percentage 0 spinning around like an atom.
Yep, that's the one. That's the one. Okay, so this is just my FORTH interpreter running through some tests. So I've got them basically. It's got some unit tests running on a emulated Z80, running in a browser, running in JavaScript ultimately, but it does actually work on the Z80 itself as well. Then after this project, I started to become interested in virtual machines in general. And I was thinking about what I can do in something that's a bit closer to what I do as a day job. So I started to look into the fact that we now have we've always had, for a very long time, we've had JavaScript in the browsers of everybody's machines. A lot of people point out that, you know, JavaScript is a scripting language, which is not the fastest thing for many applications. It's certainly fast enough to run, say, an email program or something like that. But when it comes to actually writing something like a video game or a video processing thing or a cryptography algorithm, people have been wanting to run native speed code. So something that got added to the browsers over the last 5 years is, and particularly became available since 2017, is a thing called WebAssembly. WebAssembly is a virtual machine that runs in everybody's browsers. It's also available on the web servers that run Node.js. And so one of the tasks that I've set myself but haven't completed yet is to write a FORTH interpreter for WebAssembly. So to give you a bit of background, I've I started building tools for building things in WebAssembly. These tools are available. I've got some links at the end of this presentation for those who might want to dig a bit deeper. The point about WebAssembly is it's its own language. It's an assembly language, which means it's quite tedious in its own way. And I've been building tools to just try and make that a bit easier. To give you a demonstration of the raw processing speed that is possible, you just wouldn't try and do some things that we routinely would do in machine code on a microprocessor in JavaScript. It's just not able to do things at that kind of speed. So to give you an example, I have implemented this in raw WebAssembly. It should be pretty familiar to people who have ever done any graphics programming. This is Conway's Game of Life. And you can see here, and I hope that you can get a sense of the frame rates that are coming through here. This is the Game of Life, and it's a 500 by 500 pixel array that's being processed at 60 frames a second. The kinds of speeds that I would have dreamt of on a Z80, but quite easy to do on a modern microprocessor. But the point is that you can write this and ship it in your web page now. So anybody who can see that URL above would be able to click on that link and bring it up on their own machine. And that's one of the core things about WebAssembly, that I think it's an interesting target. It's not being heavily used yet, but I'm thinking it's a very good target for programming, and I'm in the process right now of developing a fourth for it. Of course, I've been beaten to the job, so there's actually is a fourth already in existence that I think is pretty good, called WA fourth, which has been written for WebAssembly. And if you go to that URL, which again, it might be hard for you to read off your screen right now, but I can post these URLs into the Facebook chat. This is a fully fledged. Oops, this is a fourth. So you know, it's all the usual stuff. And you know, I'm pretty impressed with it. I've been just playing around with it so far, you know. Sorry, I'm just going to do a classic piece of code everyone should be familiar with. Oh, up to and there we go. So that's running in WebAssembly. What I'm wanting to do is to get my Game of Life operating under fourth in WebAssembly, just to test this sort of process out and see what the maximum sort of speeds and optimization can be achieved. But like I say, that sort of stuff is it's a little bit in. I haven't completed all of these tasks yet, so. I'll just say that some of these things are available on the web for you right now. And so I've got a series of links here, which I'll paste up. I'll paste into the Facebook, into Facebook after this presentation. But anyway, that's pretty much all I have for you today. But like I say, I'm planning to have a bit more in the fourth side of things completed by the time we do another one of these.
Brilliant.
That's me. Thank you.
Wonderful, John.
Thank you. I'll stop sharing my screen if I can work out how to get back.
I'll remove the screen.
Oh,
This share
there we go. Done it. Okay. Thank you.
You could post those links directly into the chat if you'd like to do that.
Yeah, it's a good idea. That's a good
Thank you
idea.
very
I'll
much.
do that right now.
As well, yeah, of course.
Yeah.
Thank you, John. Very cool demonstration. Now we go to Taipei to Mr. H.C. Shen.
Hi, everyone. Do you hear me?
Yes.
Yes.
Okay, good. I cannot see my video, so I don't know if it works. I got to share my screen. Just a moment.
Yep.
Share screen.
I think your video is not.
Oh,
Yes,
no,
you're doing your
no.
laptop.
Yeah, yeah.
You're doing your
Yes.
laptop or you're doing your camera.
Okay.
You
You see
can see
the
that?
We see that.
Yes. Yes,
the
we do.
video? Okay.
Yes.
Perfect.
What I'm going to show you is application of FORTH on a CAD software named Pro-E before, and it is now called Creo Parametric. It is a CAD application for ME design. Like we build the computers, the case are very difficult for, there are many problems like thermal and radio, you know, for handheld devices is also, there are many things to consider. So you need a CAD, computer-aided design. So the software is very expensive, and like Excel that Excel provide VBA and Pro Engineer, the CAD software provide a toolkit for plug-in, so you can design your software to improve the usability. So here goes my demonstration. Here, this is a DOS box, and I run the FORTH on a DOS box. Let's do it. Okay, run through a batch program, and this is okay. Here I explain what's it. It's like a VCal, right? Apple II spreadsheet versus Excel, and Excel provide a VBA, and the CAD software is like AutoCAD. Everybody knows that, and this is the Pro Engineer, okay? And I provide FORTH like Excel provide VBA. Yeah, this the simple explanation of what am I doing. And here I explain that every word in my FORTH has a help message and a command here to show the result that will be shown, that will be used later. So I make a simple demonstration of them. So hello, hi, and this is the help message. Okay, and 1, 2, 3 plus 4, 5, 6, the result is decimal and hexadecimal. Okay, and now I'm going to show you the FORTH work on real world. And now I am including the package from outside the FORTH, and then start. Creo Parametrics is the CAD application, the CAD software. And now from DOS box, I start the CAD software. That's interesting because it's like start Excel from a DOS box. Okay, now it's running. Pro Engineer start is the function within my FORTH that starting the CAD software. So it's running now. Okay, now I start the CAD, and this is the CAD, and it works. And then I close it. The start and close seems like doing nothing, but everything can be done in between. Okay, that's it, the first demonstration. And on the other hand, I can call undocumented functions of the software, of the CAD software. And there are many, many functions, 5,000, over 5,000 functions provided from the CAD software Pro Engineer. Many, many, many of them. And because I can list all of them, and I found that some of them are interesting, they are undocumented in their website. And I can understand and I can guess how to use those functions, although they are undocumented. And through my FORTH, I can use them. Okay, I tried to, and it was done. So let's try to call it. This is a string, a wide string converted from lowercase to uppercase. Very simple, but it's undocumented. And this is the entry point. I can find the entry point of the undocumented function, the entry address. What's shown is decimal and hexadecimal. And through the API word or command, I can introduce the entry point into a fourth word. This is the function, pro W string to upper. And now we are making it a fourth word with help message. Okay, this is the help message we just typed in. And now making a wide string, a wide character string. This is a wide character string, okay, and type it and dump it. A wide string, wide character string occupies 2 bytes for 1 character. So this is a W character string, yeah, in lowercase. And the upper is a memory area. It's empty at begin. And now I call the function, the undocumented function to do it, and the return code, the return result is 0, that means successfully. And now it becomes an uppercase. So this is how we can call the CAD's internal functions. On the other hand, we can call the Windows API. So we can link the 2 different words. I think the Windows API is much easier. So this is just a demo for everybody. And the problem with the CAD software is that it's license protected. So in my company, if actually we have many engineers to join the developing, but they can't because their license are limited. So through software, we can do, we can open the window for many other engineers to join our work developing. This is the good point. So thank you.
Wonderful, Mr. Cheng.
Thank you.
Yes, thank you.
Please, everybody, use the time, short time after the speakers for making questions, because this is a new area for me. I never seen CAD operated by FORTH, only FORTH cats, but probably you have questions, everybody.
I don't know if everybody can hear me, but I believe one of the big CAD companies, AutoCAD, used to have Lisp as a glue language. I don't know if that is still true.
I think it is.
Is it still being used? Because I know a chap here in South Africa worked for an engineering company selling motors and pumps. And he made a huge name for himself developing a routine to develop in CAD automatically the design of the bell housing to marry a motor and a given pump. And this work reminds me of that.
Lisp is from AutoCAD.
Yeah.
There was also a FORTH cat in France.
Okay.
The company still exists, FORTH cat.
Mm-hmm.
Okay, somebody else with questions?
Maybe one remark. If you know Blender, this is an open source software, Blender. They use Python, not Lisp or FORTH. So this is very interesting for us because we use it for teaching for kids to get them into the 3D worlds or even in object orienting and so on, programming. So the task is that we say you have to program something and this have to automate the Blender program. And the best program will win. So we had very nice results, and I think it's very suitable for kids. We're starting with 13, 14 years old, and we have concluded this in Germany since 4 years. And we presented the winners always at the PyCon, so the Python conference, or even at the EuroPython. This was just a remark for how to get kids to get into programming. Okay, thanks.
Cool. Our next, if there are no questions anymore, our next participant is Bernd Ullmann from Germany, the analog computer man.
Hi, thank you very much. I hope you can all see my shared terminal window. And I would like to talk 10 minutes about a simple programming language which a friend of mine and I have developed over the last more than a decade by now. I was always intrigued with the beauty and simplicity of FORTH, but what I was missing were the complex data structures which are supported by APL. My personal favorite programming language, sorry to say this, still is APL, but APL has its quirks. The horrible character set, the problem of getting a working APL interpreter, and so I wanted to create a blend of APL and FORTH. And that is what Lang 5 is, and I will show you how it works. Lang 5 itself is written in Perl, by the way, so do not expect it to be very quick, but expect it to be very beautiful with respect to the programs you can implement. I think it would be best if I show you two simple examples. First of all, let us, for example, simulate the throwing of a dice. We have a 6-sided dice, and I would like to throw this dice 100 times and compute the arithmetic mean of the outcomes of these dice throws. So what I could do, for example, is I could push a 6 on the stack and apply a special command, $, which generates a pseudo-random number. And if I do this over and over again, I would get different pseudo-random numbers. Pretty simple, not exciting. But the interesting thing of combining FORTH with APL features is that I could, for example, easily create a vector of, for example, 10 value 6. Now I have a vector which is sitting on top of the stack. It was sitting on top of the stack before I printed it with a dot. I have a vector with 6 scalars, scalar components, each having the value 6. And I can apply the word question mark, which generates a random number, to every element of this vector just by applying it to the vector as a whole. Doing this results in a vector like that. So now I have created 10 pseudorandom numbers between 0 and 6, excluding the value 6. I could now, for example, apply the word integer to this whole vector and get an integer vector with the outcomes of my simulated dice throws. But these run from 0 to 5 instead from 1 to 6. So I will add 1 to every vector element. And so I can create a vector with 10 pseudorandom elements between 1 and 6. You see, no loop, nothing, just linear algebra. And to compute the arithmetic mean of this vector, I have to shrink this vector down back to a scalar. And this is done in APL style with an operation called reduce. And the idea is I would like to apply a binary operator, a plus, between each 2 successive vector elements. And I can do this if I push a plus operator on the stack. Note the single quotes in front of the operator. This prevents the interpreter from interpreting the plus as an operation and instead just pushes it as an instruction on the stack. Applying the reduce operator will then yield the sum of all elements of this vector. Still no loop, nothing at all. The only thing I have to do now is divide it by 10, and I get the result, the arithmetic mean of throwing a dice for 10 times. Of course, that's not very interesting, but it gets a little bit more interesting if we define a new word. I can, of course, extend the feature list of lang 5 as I can extend the vocabulary of a traditional fourth interpreter by defining new words. And you can do a lot more than I do with these simple examples here. You can, for example, define unary and binary words, which you can then, for example, apply with reduce to elements in vectors and matrices and the like. But here I will restrict myself to simple applications of word definitions. So I could, for example, put all that what I did manually in a new word, throw dice, and this will expect a number on the stack, which denotes how often I want to throw my dice. So I have a 6 and over and reshape my, scalar into a vector, apply the pseudo-random number generator, discard all the floating point parts, add 1, reduce it to a single value, swap the remaining 2 scalars on the stack, divide it, and I've defined a new word. And now I can, for example, say 100, throw dice and point, and I get the result of simulating throwing a dice for 100 times. So I have all the advantages of APL, but I also have all the advantages of Forth. And time permits, I'm 5 minutes into my 10-minute talk to show you a second example. One example I like very much personally. I have to admit, this is not very fast. And the example to follow is extremely slow, but it's very, very elegant. And the basic idea is not from me. I think I've borrowed it from Alan Perlis. What I want to show you is how to generate a list of primes, for example. I would like to generate at first a list of primes with all prime numbers in the interval ranging from 2 to 10, for example. And to this, I would first generate a vector. 9 iota generates a vector with 9 elements with as an arithmetic arithmetic sequence. One element is just incremented by 1 to yield the next element. And I would like to have a vector spanning from 2 to 10, not from 0 to 8. So I just add 2 to this vector and get a vector from 2 to 8 to 10. I could now duplicate this vector, and now I have two vectors of the very same structure on top of my stack. What I can do now is I can perform an outer product. I have two one-dimensional data structures on the top of my stack, and I will perform an outer product, thus creating a two-dimensional data structure, effectively a multiplication table. So if I do this, I have a multiplication table without the column and row number 1. And the interesting thing of this table is this table contains everything but not a single prime, of course, since every element in this table is at least a product of 2 integers. So no element in this table can be a prime number. So what I could do to generate a list of prime numbers now is I could, you have seen I inserted another dup to duplicate my original vector. I could now check which elements in my original vector are not contained in this matrix. Here I have a binary vector that tells me that the element number 2, the first one, is not contained in this matrix. Correct, since it's a prime. 3 is also not contained in this matrix. Correct. 4 is in the matrix, but not 5, but 6. 7 is not contained, 8 is contained, 9 is contained, and 10 is per element of this matrix. So if I negate this vector, I get a 1 at every position where I have a prime number. And all I have to do now is create a third copy of my original vector and use this copy to select all the elements which have a corresponding 1 in the selection vector. And what I get is, ta-da, a list of primes between 2 and 10. And I can, of course, extend this to a list of primes between 2 and 100 just by enlarging my original vector. And you see I get a list of primes between 2 and 100. The interesting thing of this is, due to the APL-like features, you basically never need any loops at all. You also typically do not need any conditionals at all. All the things you do with basic linear algebra. The disadvantage of this approach is it's pretty slow. For example, you have seen if I compute the list of primes in between 2 and 100, it takes a short moment of time, and that's a 4 gigahertz monster max, so to speak. And the reason for this is I have to create a matrix with 10,000 elements on the fly just to perform an is element of instruction on this matrix. So it's not fast, but it's, at least in my humble opinion, a pretty beautiful approach to doing explorative mathematics or the like. I personally really use this language in my daily work. I even used it at customer locations for doing analysis in financial mathematics and the like. And if you are interested in this, you can see and download this at that link.
Okay.
GitHub.com /Bernd and then lang5. I will post it in the chat window as well. Thank you very much for your interest, and that was my 10 minutes worth of talking for today.
Wonderful, Bernd.
Excellent.
Well done. Thank you. Clap, clap.
Thanks a lot.
They're definitely out of the box ideas. Well done.
What's the way you store that vector? Like, obviously traditional forth just tends to have, you know, normal integers and double integers. So what sort of approach are you taking?
Yeah, I heavily use all the data structures available within Perl. That was the reason to select Perl, or I could have done it in Python as well as the underlying language. So I can, for example, inherit things like undefined and don't have to take care of it. So I only implemented basically the forth structure around the APL instructions, but everything else is done in pure Perl.
That's cool. Yeah, understood.
2 cents of Charles Moore, when invented forth, one of the first installations installations of forth was over Fortran.
Oh, I didn't know this. Okay,
Yes.
that's impressive.
So you are following the same path, and this is the interesting part of FORTH. Mixing two languages,
Yes.
you have a terrible weapon, no?
Yes. Okay,
Yeah,
thank you.
just point it the right way. Yes, that's good. I like that because it's similar to the kind of programming that I like to do. You know, more functional sort of stuff like that. I'd like to see more of that in FORTH.
Barend, Peter introduced you as a person involved in analog computing.
Yes, that's right.
How do you mix the analog computing and something like FORTH?
That's in the pipeline as of now. The idea is to implement a FORTH interpreter on top of our hybrid controller. We are about to couple analog computers with digital computers, and as of now it's a pretty large mess of a lot of AVR assembly language, C, Perl, Python, and whatever. And the idea is to implement a decent FORTH interpreter on the hybrid controller that is part of the analog computer, so you can program the overall operation of the analog computer in a more or less high-level language. So that is where FORTH comes into play.
I was not aware that analog computing is used at all anywhere still.
We are currently developing a modern analog computer on chip. So we are developing a reconfigurable analog computer in the CMOS process, which will be, for example, applicable to high-performance computing problems. Since if you have problems described by sets of coupled differential equations, analog computers are still pretty much faster than traditional digital computers.
Okay, yeah. Very interesting. Thank you.
Thank you very much. So I will myself
yes,
now.
Please.
I had a question. So are you using something like an FPGA, but it's an analog FPGA?
No, we are not using an FPGA. We are developing a dedicated CMOS chip, which contains all the elements of a reconfigurable analog computer. So we are really developing a new integrated circuit.
Wow. Okay.
Awesome.
Bernd is the new Charles Moore.
There you go. There you go.
Too much of an honor. There can't be a second one.
Yeah.
Well, guys, this is excellent as always. My computers are fake. This is a bitmap, but Bernd's are real. He's behind. He's in the front of a wall. A wall behind him is real.
It is real, but in this case, it stands one floor below me. So this pretty much masks the mess in my lab at the moment.
Okay.
I have one more question. So are you going to implement, I mean, FORTH would be an ideal language as the interface between the human and your, so FORTH is going to be your interface language to your,
Yes.
Will it be on chip or off chip?
That is a good question. We are currently debating this in our company. I personally would prefer having it off chip, since I don't want to have any steep clock signals on the very same silicon as my precious analog hardware. But on the other hand, there are many applications which are ideally suited for a system on chip design. And this would, of course, force me to include a FORTH program digital controller, which takes care of the configuration and parameterization of the analog computer. So we are still debating this.
Fascinating.
I see Dr. Ting is with us. Hello, Dr. Ting.
Hello. Yeah, I have trouble locking.
Well, now we have Daniel Kearney. Are you there?
Yes, hello.
Go ahead, please.
Okay. So first of all, Peter, thank you for inviting me to the group. And hopefully you can see my screen. Yeah.
Yeah.
So the question Peter asked me was why FORTH and why green array chips? So it will be, well, a little bit of personal history, if I may say, but it's for 10 minutes, so hopefully you will bear with me. So everything, oops, yeah, a little bit of introduction. I live in the Czech Republic. My education is in chemistry, and mostly I worked, and I still work for pharma industry. So electronics and programming is just my hobby. There are great advantages to be only hobbyist, as you will see. So why FORTH? Everything started in 1984. I was a kid and I was attending electronics club. And there I've seen first time in my life this computer. That's a Czechoslovak computer SAPI1. It was based on a clone of Intel 8080, modular computer with a backplane bus. And well, it was miraculous for me. I was not completely, it wasn't new for electronics. My father is actually a hobbyist as well. And he was a subscriber to this magazine. That was a Czech magazine for hobby electronics, mostly about analog stuff. But from the beginning of 80s, they started to put a supplement dedicated to microelectronics and microcomputers. And incidentally, in '84, this July issue included the first of a series of articles about FORTH programming language. So that was actually the first language I've seen. And I learned it from these articles, but I didn't have computer. 3 years later, I've been already in high school. And since even it was chemistry, what I studied, electronics was my hobby at that time. And I tried to buy some books. And mind you, Czechoslovakia was a communist country at that time still. So these are two books in Czech I could find on the Czech market about microprocessors and microcomputers. And the one in English, I got an aunt living in Canada, and she sent me this book. So I didn't speak English at that time, but it was interesting to have the book anyway. What was better is that thanks to my aunt, I also got my first computer. And that was Timex 2048, which is a clone of Sinclair ZX Spectrum. So I became Spectrist. And the best of all, I could run FORTH on that computer. Unfortunately, I had no documentation. So what I did, I completely disassembled FORTH to understand how it works. So these were my beginnings. In '93, it was after revolution in this country, and I've been already in the university. And that was first time I got access to internet. And suddenly I felt great because I could read all those excellent books about FORTH and magazines and really to learn about FORTH. So this was good time. And also I could get access to compilers for PC. So I tried many of them. F83 is my favorite, and frankly, it runs under DOS, but I still use it for my projects. About 10 years later, I made my first workshop at home, and I started to play with microcontrollers from Atmel and Freescale. And I also designed my own FORTH systems. And what was very influential was a series of articles, probably everybody knows, from Brad Rodriguez, Moving Forth, now available also as a book. And I did all this stuff to play a little bit with robotics. So this is my first mobile robot I made. It doesn't exist anymore. But I still like robotics, and there are several robots in different stages of progress. A little bit later, I started my lifelong project, and that's a retro computer based on original Motorola 6809 processor. Actually, this these components, they are from old computers and instruments. So I buy them on eBay and then I really use them. So this is the first board with CPU and memories and stuff like that. And I also wrote an FORTH that is inspired by F83 and Chemoforce from Brad Rodriguez. And the chassis you see on the picture, this is actually the real chassis from the SAPI1 computer, from the first one I've ever seen. And I use this chassis to place boards inside. So I do those boards myself. And well, you see it's 10 years and I only have one board. So it takes time. So why I use FORTH? Well, it was love at first sight, definitely. And probably for that reason, it comes as a most natural language for me. Even if I learned other languages like C, C++, and Pascal and whatever, this one is really the best I can use. As I said, as a hobbyist, I can choose FORTH. Because most of you who do programming professionally, you know that usually say I work in C, C++, but I use FORTH for my projects or to think in FORTH-like style. But I'm not really forced to use other language, so that's really the reason. You all know these arguments. It's interactive, flexible, gives total control. That's why I like it so much, and it's fun, definitely. So now the second question, how does green arrays fit in that history? So from the time I could get to the internet, I was following Chuck's projects. Not very often, but I really did. And I was completely confused by ColorForth. I tried, but couldn't use it. I was bewildered by multi-computer chips, but it was fascinating. And in 2013, I found Green Array's website, and that was really a turning point because there was a comprehensive documentation. So I could study about the chips, and also there was still is ArrayForth Institute. So I could learn about how to program those chips. And the most of all, there was this soft sim. So even without having the hardware, I could try to write programs for GA144 and then see how it works. And then browsing on the internet, I found this 2011 Force Day video with Greg Bailey, and he was proposing excellent thing. He said, come to Incline Village for a week or two, program, do an application node, and as a reward, you will get eval board. And that was great. The problem was I couldn't go to the USA to do that. So I started to think what to do, and I was thinking about a PID controller for motors. And so I write this software, and everything was running well in SoftSim. And I contacted Greg and said, look, would you like this app node? And he said, yeah, that's interesting. And I said, I have one problem. I can't run it on hardware because I can't really afford to buy $450 eval board. But if you turn it the other way around, you send me the board, I will do the app node. And great thing is he agreed. So the year after, we had this application node. And also it was how I started to do presentations during Force Day. So the first one was about controlling motors with PID controller and GA144. And the rest is history. The year after, it was about near field communication using GA144. And next year, there was this presentation about digital image processing. And I really learned a lot of stuff doing those things. And 2017 was really excellent year because we were traveling with my wife to the USA for holidays in November, incidentally. And I was able to attend SVFIG Force Day meeting in person. And I really liked it very much. I did this presentation about echolocation, but I also met all those fantastic people I knew only online or from email. So that was really great time. Next year I did presentation about heart rate monitor. That was fun because I really had electrodes attached to my body here in my room, and my wife was scared what I'm doing, you know, wires everywhere. And I was really measuring my heart rate. But the application was mostly about how to measure energy it consumes. So that was focused on that. And last year, maybe you've seen the presentation about how to connect USB keyboard to greenery chips. So why I like green arrays? Well, it's exciting, and working with green arrays is very satisfying. I like the idea that you, with green array chips, you factor your problem not only to different words like we are used to in FORTH, we factor problem into hardware, into different computers. The computers are small, and it's kind of reminiscence of old 8-bit computers I'm very fond of. So that's also a parameter that's important for me. They are small and simple. And limited resources forces you to look for efficient solutions, which is also something I like very much. That help, yeah, green arrays help me to meet great people. That's a big advantage. And I had a lot of fun with that. So I'd like to finish my short presentation with this quote from Richard Bach, because what I'm still doing, I'm still learning stuff about green array chips. I'm doing things with them, and hopefully with my presentation, I'm teaching others. And when it comes to presentations, I would like to invite you for this year, FORTH Day, November 21st, where I'm going to talk about Etherforce revival. Maybe you remember if Etherforce was something Chuck was working on a couple of years ago. And I think it was 2010, 2011, he gave some presentations. So now the system is complete, and I'm gonna talk about that in, well, month time, something like that. Thank you.
Thank you very much, Daniel.
That's excellent.
And that was very interesting, the amateur approach. What was your university training, Daniel?
Well, my background is chemistry, and more specifically, it's analytical chemistry.
Oh, okay. That is quite a world apart.
Yeah.
But he's been in electronics his whole, since you were a teenager, into electronics and computers.
Yeah, right.
Yeah, similar, a bit like similar background. I was interested in computers before I could afford a computer. Just getting books and reading absolutely everything I could get, you know.
Yeah, that was it. I had a lot of computers on paper only, a lot of schematics, you know, and thinking about computers. So with my F/9 project with this 8-bit computer, I actually, it's like my dreams coming true from childhood. So that's the reason why it doesn't matter. It takes so long time.
I have a question.
Yep.
So when you try to use the GA144 and you're solving problems, it's quite a fascinating approach, because you have to, like you were saying, factoring the hardware. Where does that architecture trip you up in solving a problem, and where does it, you know, and where is it a benefit in solving real world problems?
Well, one thing is that with the last project with Etherforce, I realized that green array chips are good for something I would call linear problems. So processing data is a good example. You have some data like analog samples, you digitize them, you process them, and then you have some output. So it flows. That's really easy, because you think like, I have to do ADC, then I have to have a filter, then I have to have, you know, whatever. These are modules. With projects like Etherforce, where actually there's no flow of data, it's like action of the user. You type something to the keyboard, and it has to react and does some work. It's more like spaghetti, you know. So that was really a surprise for me, but it's feasible. So you will see next month. Factoring into hardware, actually, what I do, I always draw the layout, the floor plan, and I think in these small rectangles, and I put different names. I say, okay, this will be ADC. Here I have to average 10 samples, so that will be another node, because there are many nodes. You have really a lot of real estate you can play with. And then I start write programs for these computers, and I slowly see how they work. And sometimes I have to go from one node to 2 or 3 nodes, because it's too big problem for one node only. So
Daniel,
this way it evolves. Yep.
Daniel, it was fantastic. So we will participate on the fourth meeting from SVFIC and hear your talk. And then you will prepare more talks for the group, for this group, and probably lessons, classes.
Yeah, if there's interest, yeah, why not? I think I have a lot of material, so yeah, we can think something else about.
Wonderful. We go now to Pablo in Argentina.
Thank you.
Hi.
Hello.
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 You hear me?
Pablo.
Yes.
Yes.
You see my screen?
Yes.
Well, I am Pablo Reda, developer of R4 and R3 language that derived from Color4. I am interested in knowing why they are few for programmers, and I note this. The time that I had to develop program for limited or specific hardware, for example, a magnetic card reader, I realized that development is much more pleasant and enjoyable. The possibilities are limited. There is a memory map that is known. Dealing with hard is direct. There are no intermediaries. The options are few, but well defined. In this context, they are many for program. But when developing system for PC or for the web, the situation changed a lot. In a talk, Charles Moore explained that what happened is that they start to add layers or abstraction. They are unnecessary. I see that they are added for different reasons. To supposedly make it easy for programming, to supposedly make for more secure, because they are someone who want to sell something, because someone come out with a great idea. All these layers enlarge the problem to be solved, and in my turn building an application into hell. And this is where FORTH appear. The big advantage is not the size of the interpreter or the compiler. Nobody cares about Facebook page being almost 3 megabytes, nor the speed of execution. The machines are so fast that when I replace a division by a bit shift, I feel almost guilty. It is worth it. I think that is a great advantage. Is not in the side of the machine, but in the head of the programmer. Finding an error in 100 lines is far better than looking for it in 10,000. FORTH don't work with a contract and a lawyer to put a number in memory. FORTH take the programmer seriously and give him the freedom to do whatever he wants. It empowers the programmer for both better or worse. A FORTH programmer is a bit less replaceable than other language programmer. Look for the specific of the problem, not the generalization. Good programming practices are generalization that does not help, and they even magnify the problem and make it more complicated. I understand that the abundance of speed and memory in the machines end up impairing development. Nowadays, there has been an increase in the number of virtual retrocomputers, which are very limited in many aspects, but they offer a phonic programming environment. Instead of using all the new features coming out continually. I believe that in FORTH, there is a direction that today is hidden by good programming practices, mechanisms that simplify models, and generalizations that simplify algorithms. Going forward somehow means getting rid of a lot of apparent advantage that have been accumulated over the years, and this a great filter for programmers. In FORTH, there is no shortcut. You have to understand how this works to master it. I think this is the reason why we are few programmers, but I am actually not sure about that. Thank you all. Thank you, Peter.
Thank you, Pablo. Pablo, ideas are interesting for us in the next meetings. Start chatting about this, start talking, and discussions, new discussions. Next participant is Thomas Fabula from Köln, Germany.
Hello, Peter.
How are you?
Thank you. So, you can give me the screen, or should I?
Go ahead.
Can you see my screen?
Not yet.
Can you see my screen?
No, not yet.
No.
Bildschirm freigeben. Now?
Not yet.
Yes.
Yes.
Now.
Yes.
Okay. So thank you for inviting me, and we'll make the presentation models. Can you see it now?
Yes.
Yes.
Okay, I have to. Then.
Just disappeared.
So now you can see it, yeah?
Here we go. Yes.
Yes.
Yep.
Starting in the, okay. So.
PowerPoint presentation, good.
You can see it, yeah? So thank you for the online conference today. And as you know, software is eating the world. I have adapted this to FORTH software is eating the world. In fact, I started FORTH in the 80s. As I mentioned before in talk with Peter, I studied physics in Bonn, starting in 1980. And as you know, Bonn was at that time the capital of Germany. And today the university is 200 years old. And at that time, in the 80s, 90s, FORTH was very appealing to get into the physical world because of the measurements and for data acquisition systems. So we have a very good physical institute. Maybe you know Wolfgang Paul. When I left the institute or the university in 1887, he got 2 years later got the Nobel Prize for Physics, and he was awarded for some special spectroscopic things. I was also working on this, but in another group, and this was a very good motivation because our faculty of math and natural sciences was really good. So this was a topic of my diploma thesis, and the task was to build up from scratch a real-time data acquisition system for high frequency and also for laser spectroscopy. And we use this for atomic spectroscopy in the Applied Physics Institute department. And we had a very old system. This was an old Z80, Zilog Z80 system. And before this, we also had a Digital Equipment Corporation. This was a PDP-8 system. So this was, let's say, an analog computer, not analog, but very discrete. Yeah. So it was from 1968, I think. So the thing was that I should build up a modern, at that time, PC, XT, extended technology, coupled with a slave computer. And this was a Europa card bus system. So this was modular. And we decided to take FORTH because of the real-time capabilities. And we needed some acquisition rates in the upper kilohertz range. And the thing was that I built up the system, we programmed it, and also made some measurements. And this was to verify the functioning of the system. We took the hyperfine structure spectra of zirconium, and I wrote also some simulation programs, but this was a high-level language with Turbo Pascal. So this is the experimental setup. What you can see here, it is for measurement of the hyperfine structure of, let's say, zirconium. We had an argon ion laser, dye laser, and we had a frequency control about this this Z80 laser interface. And we had the hollow cathode tube here where the gas was under test, and the whole data acquisition system was built by me, and it was the main topic to see this and to get a new experimental setup and new experimental possibilities. As you can see here, the system, I won't go to the PC because this is more than 30 years old, but at that time this was appealing. It was just the XT, and after this was the 80 advanced technology, and IBM was the de facto industrial standard. But we used the Z80 because this Zilog CPU was very robust. We had good software for this, and we had already from the electronic department a FORTH kernel for this. So I used FORTH on the main computer, on this host computer on PC, but also used this FORTH on the subsystem, and implemented a FIFO, first in, first out parallel transfer possibility to steer the computer and the experiment, and to have an interface box where we had some different counters and some frequency, voltage to frequency converters, and so on, and some I/O channels. So this was a very versatile interface box to several experiments. So here you can see it. We had some photon counters or some error signals, and we use this, I will go to this more in detail, to have a very cheap analog to digital converter. And we connected this to a market cavity who give us the frequencies of to compare it from our measurements. And we get this into our Z80 subcomputer to get it later into the main computer. So we get the main signals from the experiment through analog this setup. And the thing was that we had a TTL output. So we had a very easy way to have an analog to digital transformation by using this VFC62 chips. At that time, this was, I think, a very good idea. And we had to implement this, and it was very successful. Another thing you can see here, we had the fields, also the first in, first out measurement these devices connected to parallel ports of the PC. And this was a direct connection. So we could have a very high transfer here for data transmission. So during laser spectroscopy, we could focus on the real-time capabilities of the subsystem, because as you know, the PC has some lag. It is not real-time capable, because some of the interrupts are for the clock and also for the RAM refresh. So we couldn't use this. So we combined both worlds, because we had a lot of know-how in the 8-bit controllers on the one hand, and on the other side, we used, of course, in the 80s then, the upcoming PC technology. What you can see here is a terminal program what implemented in LMI FORTH 83. This was, I think, version 3.1. Maybe Peter, you know it, or the other guys. And we had a host here, and this was running in an own mode, the slave system. and we could trigger it and had to steer it by this PC. What you see on the next slide is a memory map of the Z80 system. We had here the force kernel, then the measuring program itself, some data and comments. This was a data range, and we had some for the force buffer, and this was a normal setup of, I think, 64 kilobytes. Here you can see some timing diagrams where we were sweeping the laser frequency up, and we were counting here. And on the other side, we had some inputs from the experiment, but also from the calibrating gate, so we could see which are the signals and how to get this frequency, where are we in the frequency range, and to get the right information and to have a proper data set for later for the analysis. Here you see a hardware setup. This is the interface box. We had some cards. As I mentioned, this was a ECB, called in German Europa Card Bus. I don't know whether you know it, or at that time it was very well known. Here you see double Europa format. I think this is VME was, yeah, the name was VME. And we had some of the cards implemented in here. And we used also the same cards we had used before in the experimental setup, but the new thing was that we used a real-time capable force subsystem and combined it with a PC, because before we had a CPM 2.2 or CPM 3.0 system, and this was of course not the fastest one, and we wanted to switch to the PC world. And as I mentioned, the PDP-8, it was only historic. So a good friend of mine, he finished his PhD, but after this, I think it got to the museum. So on the next slide, you can see the connection between the PC host and a Z80 slave, the master and slave. We had parallel FIFOs, and appealing feature was that we could scan. So scanning, analysis, and display of the measured spectrum was now possible in real time, and we could divide it. So make the scans and the data acquisition on the, as I mentioned, on the slave system. And we had the mass data transfer and later the analysis and things like this, simulation on the, comparing with simulations on the PC. So this was, I think, a very good new feature. And as you see here, Echtzeit means in German the real time. This is the real time capability. Everything else was post processing, not in real time. So here are some spectra of zirconium isotope shifts we measured, and this is what we had got with the system. This was a comparison to another measurement before, and to see where are the peaks and where to look for in the experiment. I wrote also a simulation program. This was at that time Turbo Pascal. It was fully implemented on a PC. It was fast enough, and you could play with these factors. I don't want to go into details, but to see, okay, what is bandwidth and where to see or where to look for the signals. And we switched between this simulation program and during measurement to see, aha, here are some peaks and where to look for, and to have a good comparison. And I think this was also good to learn a lot of insights about hyperfine structure and things like atomic spectroscopy. So in the end, I want to conclude that this was, in the time 85 to 87, a PC-based data acquisition system was built up, and we used at that time the Z80 slave computer, and we could perform high-resolution laser polarization spectroscopy. And due to the utilization of a two-processor system, we think we had a very fast system response and could perform very fast measurements. And the real-time capabilities are within the slave computer, and the FIFO buffers were very responsible for this. And on the other side, we had standardized components, because at that time you could buy a lot of hardware interfaces and software for the PC. Of course, at that time it was very, yeah, it was not cheap, but the labor of students was cheap. So the professors used us to get this implemented, to implement. But I think for analyzing spectroscopy data, it was very good. And we had also the opportunity to add some commercial software packages later on, but this was not my job anymore, because we showed this was running and it was enough to get the experiment running. So if you want to have some more information about this, we had made also publication 88 in the Journal of Physics E. So it's about scientific instruments. There's also a link, I will send it to you. And this was the final remark. And I want to thank you, because I use this to present also in a paper at the Deutsche Physikalische Gesellschaft. We had this at that time in Bonn. And after this, I left the institute. I went to the south part of Germany, and I made some more applied physics, but in the field of microelectromechanical systems. And this was the time where microsystems were born, let's say. We had good cooperation with Bosch, and we developed sensors. You use sensors like this every day in your smartphone. And I think this was a very good basis to understand these things. And from that on, I never used force, sorry. So this is some years old ago, some decades, but it was a very powerful tool. And I could cooperate with the electronic department and also with the old guys. And I think this was a good combination for forth to have high level and a very machine. So this means on a machine level, combine it, and to have both advantages of both worlds. So this is it. Thank you. And yeah, if you have some questions, please feel free.
Wonderful, Thomas. Excellent.
Thank you. Thank you.
It's amazing. In your presentation, you spoke about, well, in the documentation, it said 4 millisecond acquisition time. That's very quick. Well done.
Mm-hmm.
I have a question, if allowed. How do you define real time?
Yeah, that's good question. Yeah.
Thomas, please stop screen sharing.
Okay.
I kind of wonder how much other researchers continue to use DOS because of its simplicity in research.
You mean DOS or what?
Yeah, DOS.
Mm-hmm.
Yeah, all DOS.
So MS-DOS, you mean, yes?
Yeah.
Yes, MS-DOS.
Yeah, the thing was, we had different institutes. Our institute was in the building of the mainframes. So we could use the mainframes for post-data analysis, but not for real-time or for experimental control. So real-time means what is sufficient for our experiments. So for our experiments, it was sufficient to have this resolution. Of course, if you look at the CERN, so high energy physics, they have another definition of real-time. But we decided to have this PC-based, or before this we had the CPM systems, and we were limited by the interrupts of the PC. So we used this two processor system. And other institute, they had some digital equipment cooperation measurements equipments, or even some extra equipment. So it was dependent of the institute who is running the experiment. But for our laser spectroscopy and atomic spectroscopy, this was sufficient and enough.
Thank you.
Okay, now friends, we have 5 or 4 presenters who will say hi for first time to the group. The first one is from a new continent. We are now on 4 continents, this group, and is Johan Kotze. Where are you, Johan?
I am here, Peter. Welcome everybody. Thanks for the invite. And I've found everything very, very interesting up to now. Fourth and me, or is it fourth and I?
Okay, but only two minutes, Johan. Only to say,
Yeah.
can you, for example, for the next meeting, are you ready for make a longer talk?
Yes, I can. I can make a slightly longer one. But I've never really worked in Forth. Forth was always a background, not even a hobby. I just knew about it and that's it. I've only now started doing a bit banging.
But now you are with the Raspberry Pi, so you can start experimenting and make a presentation. We don't are after professional presentations. This is a friendly group.
I've noticed that.
And we promote Forth. This is the only objective. Everybody can show their applications.
Yes.
We don't expect only Don is working with NASA and with the rockets, but we are on the Earth.
Excellent. Now I take that. That's good.
Okay. Thank you, Johan. Next meeting, just call me. 5 minutes or 10 minutes is no problem.
I'll do.
Wonderful. You are here with us.
Great.
Cornelius.
Thanks.
Cornelius, another one.
Hey, good morning, everybody. Good evening, or whatever time zone you're at. My name is Cornelius Keck. I reside in Plano, Texas. I've been playing around back in the late 80s in Forth. And unfortunately, most of my gear I had to leave behind in Germany. One of the things I brought back last summer from my yearly trip, sorry didn't have one this year, is a Novix 4016 single board computer, which I bought, I think, from Ulrich Hoffmann back in Kiel, back in the 80s. Not sure. It's been a while. I'm trying to get this thing working again. That means we have to break into it. Not so much from a security perspective, but some of these components are aging. EPROMs do not have a life expectancy of 33 years, so that needs to change. They need to be replaced. And then, yeah, understand this thing. That means I'm Forth-wise working to get two things going. These EPROMs read out and duplicated, preferably without the use of an EPROM, of a commercial EPROM reader burner, because where's the fun in that? You can build this thing yourself using an Arduino. The other thing, found a simulator written back in the 90s in Ball and C. Porting that thing to something current is a little bit of a slugfest. So one of those two endeavors, or maybe two, I'll be presenting on our next meeting in November.
Excellent.
And that concludes my spiel for today.
Thank you, Cornelius. Now, Joseph, where are you, Joseph?
Are you talking to me, Peter?
Yes.
Hi. Thank you for inviting me to the group. My name is Joe O'Connor. I first got acquainted with Forth back in the 1990s. I used it to, I found FPC. I used it to help with my assembly language homework. Later on, I found Leo Brody's book, Starting Forth, and also Thinking Forth. They were like my Bible. A few years later, I found Norman Smith's Until. I was fascinated by the concept. It is almost 100% Forth, but it sits on top of C or C++. Some of you were saying what a horrible programming language it is, but you can do that. And I was inspired to build my own version of a Forth by that. Instead of C++, I chose Delphi and Pascal. Later on, I ported it to Lazarus. And since then, I've taken the idea to a few other platforms or languages. These include Excel, JavaScript, Python, Perl. I have an interpreter done in C#. I haven't gotten the compiler right yet. Hopefully I will have the time to do so. Next month, I'm going to be giving a presentation. I'll be giving the same thing at SVFig a little bit later. It's on my version of the compiler. I have a few new, well, not really new ideas, but twist on ideas that have been floating around the Forth community for many years. So that's all I have to say. Again, I thank Peter for
Thank you, Joe. So you are next, you are in the next meeting in November 7th, okay?
Correct. Thank
Perfect. Who is the next? Now is Wolf. Wolf, are you there? From Switzerland.
Yes, hello.
Hello, Wolf.
Okay.
Go ahead.
I am Wolf Weigert. And well, I spent 2 years with the PDP-8E during my studies for the thesis, which ran all our experiments and was programmed in Focal, which was quite close to Forth somehow. I left physics for good to explore that fascinating new world of computers, those machines that are defined by text, literally in Forth later. I gave it a try as a freelancer and luckily it worked until today, surely thanks to FigForce that arrived in Switzerland also, the 1979, via an article in an electronics magazine, talked about words and stack, which made so much sense. The address of FigForce was included. I soon had Force 11.
One moment, Wolf. We will mute everybody and then you continue.
Muted one too many.
Wolf?
Can
Wolf,
you
you
unmute
need
yourself,
to
please?
unmute.
Okay, you muted me. I'm here again. So I was a freelancer. I had luck. I found an interesting job creating a quality control system for airborne cameras. Cameras that are still produced. I had Force 11 to do it on a PDP-11. I needed as an optical instrument, so it had data with 9 decimal places. How do you do it in Force 11? The PDP, yes, had also Fortran. I was lucky and had the Fortran scientific library. And since Force 11 is done in macro assembler and so is the library, it wasn't too, it was easy to get floating point into Force. And so it all went fine. 13 years later, I brought this system to the PC in Holland Force. And 10 years later, it was transformed to basic, Visual Basic, but not by me, by the companies that took it over. So I explored all dimensions of Force, created projects for clients, also embedded, created target compilers, was engaged by a Swiss company who sold Force computers, industrial Force computers, to give courses, and so on. Force was, every problem I had in Force had a solution, a satisfying solution, may have taken time, but there was a solution. Only one problem has remained until 1989, how to keep track of the source infos. If you have clients get the first version, the specs change, the program changes because everybody's learning. I found the solution. Have I still some time?
Wolf, it's only to say hi to the group and to announce your next presentation will be in November 7.
That is coming now. I had one question to FORTH. That FORTH is, why must the compiler create the dictionary? And I've never seen that question written in our FORTH, but it got me to Roland FORTH. And Roland FORTH creates the editor in the dictionary in the editor and brings the dictionary from the hood, under the hood, up to the desktop. That's what I'm going to illustrate.
Perfect, perfect, wonderful. Wolf, then next, we see you again in November and you will present Holland FORTH. Is okay?
Yes, exactly.
Lion, are you there? Do you want to say us hello from Malaysia?
Thank you, Wolf. That's a really interesting topic about the dictionary.
Hello?
Hello, Lion. Lion?
Yes, yes. Yeah, can you hear me? The signal is not very good, is it?
Okay.
Is it okay now?
We can hear you fine. Don't share your camera. It'll slow your network connection down.
Yeah. I think I won't switch on the video. Okay. All right. I started learning computers when I was very young, but then I think I missed out FORTH altogether until a few years ago. So anyway, I started working on something related to FORTH, not directly the traditional FORTH, as in the low-level assembly FORTH, because at that time what I wanted to do was that I wanted to find a language that I can use on the mobile phone, and eventually I took the FORTH architecture and implemented a sort of high-level FORTH in various different programming languages: JavaScript, Python, Java, Python, C++, and C, and so on, basically. So that was what I'm doing at the moment, and so I thought of a name for what I'm doing. Is called Meta Programming in FORTH, abbreviation as MI4. For those of you who knows about the story of a Cold War, MI4 is like before you had MI5 and MI6. So that's a brief introduction of what I'm doing.
Funny.
Hello?
Lion.
We can hear you.
Yeah.
You are appointed for November 7, so you will have your time for presentation. It's good enough now to say hello to the group.
Okay.
And
all right.
It's perfect. We love you are with us, and I will share my screen. One moment. Can you see my screen?
Yes.
This is about the next guys. Now we make a 5-minute break, and we start after that the class of FPGA CPU in FORTH with Ilya from Russia. It's okay? 5-minute break.
I have a quick question for Ilya. So I got the board. we need to download something before the class, don't we?
I have a completed design in Xilinx Vivado, and I will send it in source text after this class.
Okay.
I have the same. I have the same, and I will run it in hardware.
Great. Looking forward to it.
Itu bayang.
Leon, you might want to unmute your mic. Sounds like you got World War III going on back there.
Hello, Don. Don Golding?
Dr. Ting, how are you doing?
Fine. Good to see you.
Oh, it's great seeing you. Hey, I sent an email to Chuck. He responded to me.
Oh, what?
I sent an email to Chuck.
Yes.
Within the last week, and he responded to me.
Oh,
And
okay. Good.
he said he was very smoky where he is at, so he must have moved back to Silicon Valley. I don't know.
I don't know. We got all the smoke here, all the smoke originates here. Sorry about that.
Yeah, he. I invited him, to come to our meeting. We'll see if he does it.
Mm-hmm.
Are we going to do a virtual 4th day in November?
I think so. I don't see that we can operate a physical meeting,
Right. Well,
but I don't know. Mhm.
you know, the nice thing about virtual is we can have more people.
Yes, yes. The room is unlimited.
Yeah. So,
How's the board?
well, I haven't worked on it in a month. I've been working 6 days a week on the flight computer for Archinaut, which I'm finishing up. I should have it done in a week, and then I want to take a week off and just work on the board. And then get it done. Yeah. I want to get it to you. I really do.
Okay. Well, no hurry.
So yeah, you know, I've been thinking that after this board is done, what about an FPGA version?
Well, you know, it all depends upon how much does it cost for the FPGA board. FPGA board seems to get more and more expensive.
Well, you can get FPGAs in the $20 range, so that's not too bad. And
yeah, I think it's the tools. Yeah, you need tools, and I don't know. I'm out of it. Okay.
Yeah. Got it.
Yeah, but it's still interesting. I think there's lots of things can be done with that. I just don't. You know, I show you the lattice board last time. The tools are just too expensive.
Yeah, they are. Well, there's who's the other fellow that did FORTH on an FPGA? Really interested in
Bowman.
Yeah, yeah. So he was using an open source tool set. So we have to get to know that tool set. You know, we just need something to take raw source code and synthesize it. We don't need a bunch of modules and, you know,
James,
IP.
Oh, Don, James was invited. He did not respond, but he will present in any of the next meetings. I am very happy he's with us in the group. The other guy who makes FPGA FORTH is in Germany. He is probably Ulrich Hoffmann or any other friend from Germany. Can invite Klaus Kohl.
Yeah, I am super excited about putting FORTH in an FPGA. In fact, I have people at Made in Space interested in FORTH. I have two people. And if I could show them something physical working, because there's, you know, the thing about an FPGA, this used to drive me crazy when I first got into FPGAs, is you got this beautiful parallel computer, and then everybody wants to put a frickin' core in it. They want to put a, you know, some sort of, you know, sequential processor in there, and it uses a lot of fabric. And because they can't break down a problem into, you know, parallelism and then use the native tools, which is VHDL or System Verilog. So, and then the other thing is when you put a core in there, it needs memory. So now you need a memory chip on the outside of the FPGA, which is using up all your pins. FORTH is so stingy with memory, it should be able to use the memory inside the FPGA, and that's all it needs. So, and interactive programming in an FPGA, you can't do that with any tool, right?
Exactly.
So, yeah, I think the FPGA thing, I think I can sell it within Made in Space, but I think it's an area that no other technology can solve it. If you want to run C, you have to put a big RISC core in there, right? And then you have to throw in memory. And you have to have flash. You got to store the program somewhere.
And energy.
Now, when you guys are talking about a core, never mind, forth in an FPGA, are you talking about forth directly into the fabric? No CPU at all?
Yes, absolutely. That's the class. That's the class today.
Yeah.
That's
that
what
sounds
Ilya's going to
great.
present.
Because I did some cores. Dr. Shen there had the EP32, and I put that on a Brevia 2, and that sucker was nice, fast. But
Good for you.
yeah. And I tried your PDP-1. What an interesting processor. Wow. Thanks, but no thanks. Anyway, this little itty bitty thing ran a 32-bit forth with a fraction of its resources. It'd be interesting to see forth directly wired into the matrix, so it's parallel and fast.
You could have multiple cores running simultaneously. So,
right.
You know, what would be really exciting is you create like a bus inside the FPGA. You have these forth subsystems where forth, in an FPGA, you always have sequential processing at the top, right? And then it gets parallel as it gets towards the motors and sensors and stuff. So that's parallelism down there. But you always have, you know, a sequential process above, you know, all these different subsystems in an FPGA. So we make that high-level sequential processor forth, and then a bus. Yeah, I mean, that just, and then you can interactively, you know, program the thing. You can't do that with any other language. It's impossible.
Wow, that would be fascinating.
And the other thing is, you know, forth is so
What is
stingy.
this, Adrian? What is this, please? Can you? Is your microphone?
FPGA. USB plugs in. Here's the details of the chip, and supposedly I can get forth onto it, and I have been trying, but there is some difficulty. Rob in Scotland has been helping me. He has a different version of this, an earlier one, and there is some small difficulty in trying to port it from the earlier version of this to this one here. Once it's done, then yeah, tiny, and they're only worth a few dollars. And I had mine shipped from the US to here in Estonia in under a week. Amazing. But I've still got to get it to work.
That is an FPGA?
Yep, sure thing.
And who's the
the
manufacturer?
Could you
look,
put the link in the chat, please?
Yeah, there you go.
FOMU, huh?
Yeah, you just find it, and then you can. Now, I would say it's very limited, but it's a great interest. It's something to get started with, and that's all I want it for. And then when I've learned how to drive the software, then I can look at implementing something on something a bit bigger with more power to do different things. I have a few ideas that I'd like to try out that normally would be done in words, but to try put it back into hardware, make it faster and more efficient. Efficiency, not necessarily
Adrian,
fast.
do you mind if we start with the
Yeah, go.